Thanks very much for the introduction. It's a pleasure to be here. I've been dubbing my talk quantum computing, why it's not science fiction. But if we're all really, really honest with each other, science fiction and the flair of it is kind of part of why we're in the game, isn't it? So today, I am inviting you to hop onto my TARDIS. And for everyone who does not understand this reference, it's very British. Watch the series Doctor Who. It's a science fiction, long-running science fiction series in the UK. Hop onto my TARDIS to see what was, what is today, and what could be in the future. So the first place I want to take you to is the year 2006, and the place is Germany. And I was a chemistry undergrad student. It was very hot summer. You might remember the World Cup was going on in Germany. We finally became a somewhat cheerful nation. And I was not watching football because I was in the lab slogging away at the first steps of a natural compound synthesis. I was trying to get this reaction to run. It was supposed to be able to run it. It was supposed to be simple, but it wasn't. Somehow something was wrong. And I tried to vary every parameter that I could think of: temperature, solvents, catalyst, everything. It did not work. So instead of going to the party, I was stuck in the lab. And this was a transformative moment for me in my career, because I was asking myself, why can I not design this reaction on a computer, rather than having to stand here varying every parameter by hand? Why is that not possible? Well, fundamentally, it's not possible because classical computers are terrible at representing quantum systems. They're terrible at it. You need exponential computing power, exponential with the system size, to properly calculate your chemical system. And that's because, well, chemical systems, they consist of atoms, which have electrons, and these are quantum particles. So they're terrible at it. So now, next, I want to invite you to hop onto my TARDIS again, and we arrive in the year, well, I picked the year 2086, because I'll be 100 by then. I'll still be alive at a seaside place with my 7 grandchildren. And so how will this quantum computer that we're all building, that we're all working towards, how will it have changed how we do things? And one thing that we will be able to do on this quantum computer of the future is we will be able to design drugs, for example, such drugs that have very specific interactions between the drug and the enzyme it's targeting. Ibrutinib is an example of this, that you really, really have a hard time with representing classically. And this drug here, ibrutinib, is a drug against non-Hodgkin's lymphoma, a form of cancer. On a classical computer, you really don't have a chance of representing this system with sufficient accuracy. But on that quantum computer of the future, if you have a quantum computer that can do 560 million operations on about 500,000 qubits, you'll do this calculation in 2.5 hours, and you'll be able to really design the interaction between the drug and the inhibitor. The defining challenge in making this happen, and why the qubit counts are so big and the number of operations are so big, is quantum error correction. It's really quantum error correction commercially that will unlock high-value applications for us. The NISQ market is great. It's an academic market. It's wonderful. It gets us to proof of concepts, etc. But for high-value applications, we need quantum error correction. Because fundamentally in quantum systems, what we're doing in quantum computers is we work against the noise. And noise is something that is inherent, that is fundamental to how quantum systems behave because of a little thing called the Heisenberg uncertainty principle. So there's fundamental quantum fluctuations that we work against when building a quantum computer. Okay, last time onto my TARDIS, and we're going to arrive at the present. And this is what a quantum computer looks today, and it is designed to work against this noise already. This is why this machine look so complicated. Here we have a superconducting quantum computer, and the qubits are kept alive by instruments who send in pulses of exactly the right shape at exactly the right time. These are coordinated by local computers that react very quickly to what's happening, and sort of everything is managed by a central computer. That's roughly how it looks. So I liken this to a dance, where a corps de ballet keeps a qubit spinning in a perfect pirouette. And our colleagues at hardware companies have gotten incredibly good at keeping that qubit spinning. So, routinely when we work with hardware companies, we can run 100 operations on such a machine. But that's pretty far away from 560 million that we will need to run this ibrotinib example. So what do we have to do to improve it further? Well, we can improve it further. We can probably squeeze more out of it. But at some point, we will need to have something called quantum error correction. How does that work? So quantum error correction is fundamentally the process of taking many noisy qubits and transforming them into one long-lived, stable, or logical qubit. Why do we need so many? Well, first we need to encode redundancy. So in case the noise destroys our information, we have it again. We can use a different qubit that the same information is encoded in. Second, we need to use a lot of auxiliary qubits to read out the information, because as you know, if you do a quantum measurement, that sort of destroys your quantum state. So you have to have these auxiliary qubits again, in addition to the regular data qubits. And that's what we do in quantum error correction. How does that then look on this wonderful life support system that I showed you? It looks like this. So we measure the qubits. That's this syndrome generation process that's marked here, with the instruments that we have. And then we have local computers that have to do something called decoding. And decoding is the process of using the information that we read out from these auxiliary qubits and understanding where the error actually occurred. That's difficult. That's a very, very big, meaty optimization problem that we have to do. And then we have to issue the correction. This is a classical information loop, and I love that Chris Monroe said, oh, it's all engineering. This is engineering, but this is pretty tricky engineering. We have to do this cycle for superconducting systems 2.4 million times every second. That's pretty fast. And using this ibrotinib example again, we will probably generate on the order of hundreds of terabytes per second of data. And that will have to be processed through this classical information loop as well. This is the same as Netflix's worldwide data rate. So this is pretty big. This is a pretty big engineering problem. So now I've scared you a bit. What are we doing to crack this problem? Or what do we have to do to crack this problem, rather? So we think of cracking this problem in an integrated way, in an approach that we call Delta Flow OS at Riverlane. Fundamentally, what we need is a well-engineered control system that can support the scales we need and that can support this classical information loop properly. And this will be integrated very, very tightly with this decoder that I showed you. And it will be integrated very tightly with a runtime that will manage how the calculation really, really runs. This is what we call the kernel at Riverlane, at least. We need to also design our systems much better from a quantum information perspective. So we need to reduce the number of physical qubits that go into each logical qubit, which is a research challenge still. We need to know much more about noise, about layouts, about the interplay between codes and noise and physical systems to optimize this. But there is huge opportunity to reduce the number of qubits that we will need. This is a vastly under-researched area at the moment. And on the applications layer, we can also do tons. There's orders of magnitude that we can still get out and squeeze out of algorithms. And to just illustrate that last point with my last slide, through improvements on how exactly we map a chemistry problem onto a quantum computer, we have, in the last couple of years, already been able to reduce the resource requirements that we need for these chemicals, which are important in the context of battery materials or solar cells. We have been able to reduce the resource requirements by a million times and more. So I hope I convinced you that quantum error correction is important. I hope I could explain roughly what we need to do to make error correction a reality, and that we're on it. So I'm optimistic that by the time I'm 100, these chemistry students in the lab will not have to manually labor away while missing football, so they can design a chemical reaction properly. Thanks very much.